Hi guys, welcome. This is week 2, and in this week, again, you can watch it, break it apart however you want. We're going to be going through lessons 83, 84, and 85 this week. So we have 3 lessons to get through. So let's go ahead and take a look. So lesson 83, we're looking at probability of dependent events, dependent upon each other. So it's not independent events would be like flipping a coin and pulling a card out of a deck of cards. Okay, whatever you flip the coin, that has no bearing on the card that you pull out of the deck of cards. Whereas dependent events, whatever happens in the first event does affect the second event or third or fourth or how many events we're talking about. Okay, how we find that, okay, we know that when events are independent, we just find the probability of event A and B and multiply them together. Probability of flipping a coin, landing on heads, rolling a dice, and getting a 6. We have a 1 in 2 chance of getting heads. We have a 1 in 6 chance of getting 6. We multiply those together, we get a 1 in 12 chance. Here we do our sample space, but in sample space, especially the more events or more outcomes we have, can become very exhaustive. So just using the multiplication is much easier. So that's if they're independent. Okay, flipping the coin has nothing to do with rolling the dice. So those would be independent. Now, if they do have to do with each other, and the second event is dependent upon what happens in the first event, then those are known as dependent events. Okay, we'll look at some examples. 2 8th graders and 1 7th grader want to go on a trip, but only 2 students will be selected. If their names are drawn at random, what is the probability that 2 8th graders will get to go? So we make a tree diagram. Okay, so just again, sample space of all the possible outcomes. So 2 8th graders and a 7th grader. So first 8th grader, well, we can have the second 8th grader or the 7th grader, 8th grader, the other 8th grader or the 7th grader. If we have a 7th grader drawn first, then one of the 2 8th graders has to be drawn on the second. So all of these are probabilities. So the probability of getting an 8th grader and an 8th grader, well, it's either this outcome or this outcome, which is 2 out of our 6, or reduced down to 1 in 3 chance of that happening. Rather than counting outcomes in example 1, again, the sample space is helpful. If it's 3, 4 possible different outcomes, if we're talking about 50 outcomes and 5 different events, we probably don't want to draw out 5 million possibilities or something like that. So we can consider probabilities at each stage of the experiment. In the first stage, the selection of the first student was 2 and 3 of the students are 8th graders. 2 of our 3 students were 8th graders. That's what we were told. After an 8th grader is selected, 1 is taken away. Now there's 2 students left. One of those 2 students is an 8th grader, so 1 in 2 chance, okay, or 0.5 or 50%, 1/2. So we multiply 2/3 times 1/2, and then we get 2 over 6, or that reduces down to 1 over 3. So multiplication rule for events A and B that are not independent. So we have the probability of event A under the initial conditions, because that's our first event, nothing's happened. And then the probability of event B under the new conditions. So again, first student was drawn. That's event A, or our first event. Event B, now we only have 2 students left, and we draw from that. So that's a different probability, because there's a 1 in 2 versus the 2 and 3 of our initial event. So we still multiply them together, and we get our probability. And this is conditional probability. That's an example of that. Example 2, a bag contains 2 white marbles, 3 blue. If 2 marbles are selected, what is the probability of selecting 2 blue marbles if the marbles are selected? A, with replacement, B, without replacement. So that's important. If we draw a marble out of a bag, then we put it back in, shake it up, whatever we need to do, and then pull out again, okay, then it's independent. Whatever we drew on the first one, we're putting it back in, shuffling it up again, and then redrawing. Whatever we got on the first one doesn't affect the second one. So that would be independent. So that would be, we have a 3 and 5 and a 3 and 5 because we had 3 blue marbles. Okay, so we have a 3 out of our 5. 2 white marbles, so total of 5 marbles. A 3 and 5 chance, we put it back in and do it again. It's still a 3 and 5 chance. So we multiply those together and we get a 9 and 25 chance, or 9 over 25, or we could express as a decimal right there. Okay. Without replacement, so we draw a marble out and we keep it out. Well, now the total number of marbles in the bag is different for event B than it was for event A. And also the number of blue marbles is different. Okay? So the second event is going to have a different probability. So still 3 and 5. Okay? Blue, we have 3 of our 5 are blue, so a 3 and 5 chance. Okay? But we take one of those blue marbles out. There's now 2 blue marbles left out of 4 total marbles. So 3/5 times 2/4 or 1/2, we get 3/10, which is a 0.3 chance of that happening. So the probability is going down, which makes sense because we take a blue out. Now instead of having 3 out of 5 chance, there's a 1 out of 2 or 2 out of 4 chance of getting a blue marble. So the probability is going down. All right, we will look at those together when we return. All right, lesson 84, selecting an appropriate rational number. So again, rational, we know, can be expressed as a fraction. So like 1/3. 1/3 as a decimal is 0.3 repeating forever. And just because it's going on forever, it's repeating, and it can be expressed as a fraction. So yes, it is rational. If it cannot be expressed as a fraction, and it's a decimal that continues on infinitely and never terminates or repeats, then it's irrational. So for this lesson, we're talking about rational numbers. Consider how we calculate. We've done plenty of problems with tax rate. Okay, you have a 7% tax rate. The purchase was $12.60. We want to figure out what is 7% of $12.60. I think in that example, since it's money and we're working with a decimal, probably easier to convert it to a decimal. 7%, we're going to convert to 0.07 and multiply it by that. We can do 7 over 100 and do a fraction and reduce and multiply. But since we don't really operate with fractions in money, we use decimals. I think multiplying a decimal by a decimal will be a little bit easier. Now, that may not always be the case, because if the discount is 33 1/3%, which is kind of an odd discount, but we're taking 1/3 of it off, okay, that example may be easier because we can't really put 0.3 repeating forever. We can put 0.33333333 out to 9 decimals in our calculator, but there's no way to indicate that it's repeating forever. So our calculator eventually rounds it off because that's what it has to do. So this example may be easier, even though it is still money, to convert 33 1/3%, which we know we convert it to an improper fraction and multiply it by 1 over 100, reduce it down. It's going to reduce to 1/3. 1/3 times 12.60. In that case, might be easier. It probably will be easier because then there's no way to put in 0.3 repeating into our calculator or to compute that. So using a fraction, that example is probably going to be a better bet. All right. If we're looking at percents and fractions and decimals, well, we got to choose a rational number. 40% of 1/2 of $12.60. That same number we started with up here. I would personally do decimal for this one just because this can easily be converted to 0.4. 1/2 we know, or we could quickly figure out if we don't remember, is 0.5. So we multiply 0.4 times 0.5 times 12.6 or 12.60, and we get $2.52. Okay, 0.4 times 0.5 times 12.60. Now 66 2/3%, again, a repeating decimal. That would be 0.6 repeating forever. So there's no way to really notate that in our calculator or even performing it by hand. So probably going to be easier to multiply 66 by 3 plus 2, and then make it an improper fraction, then multiply it by 1 over 100, or you may remember that 66 and 2/3% as a fraction. We go through all that and it becomes 2/3. So 2/3 of 5 over 6, 5/6, since that's already a fraction, we'll just leave it, of 12.60. So 2/3 times 5/6 times 12.60 multiplies out to be $7. So even though, yes, the money is in decimal, it's easier to keep these two numbers as a fraction. So if we have three numbers, one's a decimal and two of those three we're going to make a fraction, probably easier to keep it in terms of fraction. In a public opinion survey, 180 of 280 women surveyed agree or strongly agree with the mayor, while 150 of the 275 men surveyed agree or strongly agree with the mayor. Which choice listed below is the most appropriate way to describe the results of the survey? 9/14 of the women and 6/11 of the men agree with the mayor. This again, you're political strategist and you're trying to help convey a message. You don't want to manipulate the numbers or change them. You want to be accurate, but you want to give the best representation and the one that makes most sense. So A, maybe not. If we convert those to decimals, 0.643 of women and 0.545 of men agree with the mayor. Well, I would think both A and B would be a little confusing. Well, we reduced our fractions. That's good. Must have went to math class. But did we only interview 14 women and 11 men? That doesn't really seem like a great sample size. That's not the actual survey, but it's reduced down. So that one may be a little confusing and make it seem like we didn't really talk to that many of the voters. B, a decimal, or did we not even interview a full person? I mean, what does that number represent? Whereas C, when we're talking about a percentage, 64% of women and 55% of men agree or strongly agree with the mayor. I think that one would be a little better expression just because, we didn't interview every single person, maybe that's registered voter or every constituent, but we get a good idea. 64% of the women and 55% of the men. That's not 100%, but that's over half for men and women. That shows that a majority of people agree with the mayor. That's probably a better, if you're running a campaign or something or putting this out there, you would probably go with C. It would be more clear and sound better than A and B. All right, practice set. We'll go over that together. And then the last lesson we are looking at is lesson 85, surface area of cylinders and prisms. Again, surface area, if we were to draw out the net of our three-dimensional shape, what would it be? That's going to be our surface area. So we do have lateral surface area and surface area. I believe all the surface areas that we're going to see are on your reference sheet. Lateral surface area, I'm not sure, but I'll let you guys add those in as we see them. So again, a prism, we have triangular prism, rectangular prism, pentagonal prism, octagonal prism, anything that's the same shape, top and bottom. It's a polygon, a triangle, a square, rectangle, whatever, parallelogram. And then the other base is congruent polygon to what is on the top, our two bases. So triangular prism, congruent triangle, front and back, okay, or top and bottom. Again, it doesn't matter the orientation. If we take a cylinder like a coffee can or a soup can or something, we put it on side or straight up and down, it's still a cylinder. So we refer to it based on its bases. Okay, triangular prism, cylinder. Cylinder is basically a circular prism. We just don't call it that. We call it a cylinder. Okay, so again, a soup can or coffee can, something, that's the easiest way to kind of picture what a cylinder is. So we have two circles, top and bottom, 1, 2. And then if we were to unroll this out, like if it was a label on a soup can and you took it off and you didn't rip it or anything, you would have a rectangle. So these are going to be our three shapes that we need to find the area of the circle, And this is going to be the same area, so we can just multiply it by 2, then find the area of the rectangle, add them all up, and that will be our surface area. So if we're going to look at this cylinder and leave it in terms of pi, diameter is 4, so we know the radius is 2. Okay, so pi r squared, okay, as if we're finding the area, surface area. If we're finding the volume, then we would do, we've already worked with volume, pi r squared, and then times 5. That's if we want to find the volume. Now we're looking at surface area, so we want to find our circumference. Okay, so we have 2 pi r, looking at something else. So our diameter is 4, our radius is 2, so we're going to use pi r squared. We want to find the area of this circle. It's going to be the same area as this one, right? So circumference. Okay, area of both of these, and then this we know is going to be 5, and then this is where we need to know the circumference of our circle. Well, why do we need to know circumference? It's area. Because we need to know if we were to unroll the soup can, what would be this distance from here to here? Well, that would be the distance around our circle. And we lay it out flat, it's going to form a rectangle, so that's why this is 4 times pi. Because pi times our diameter is 4 pi. And so that's just this distance right here. So area 1 plus area 2 plus area 3. So this pi r squared, 2 squared is 4. So this is 4 pi. This obviously has to be the same thing. So 4 pi. And then this is 4 pi times 5. Not 4 times 5. Again, pi is not just an insignificant symbol. It's not an unknown. It's not anything like that. We can combine like terms using pi, but we can't. It still is a number that we're multiplying by. So 4 pi and 4 are 2 different numbers. So 4 pi times 5 is 20 pi. Then we add them. Again, we can combine like terms since it's 4 pi. 4 pi, now if it's pi squared, obviously same as if it's x or y or a, b, whatever. We can only combine if it's the same term to the same value. So 4 pi, I have 4 of them. I add 4 more, and then 20 more. I have 28 pi square units. We weren't told what the units were, so we'll just put square units. Okay, example 2, we have a triangular prism. Again, just because the triangles aren't top and bottom, it's still a triangular prism. So we have a triangle front and back. So if we were to lay this out, you think of like a tent that you laid out flat, you would have triangle and triangle. Those are congruent. And then these 3 faces would be these 3 rectangles. So this one's going to take a little bit more work. This is where I said volume is actually a little bit easier in my opinion than surface area, because we just find the area of the polygon, multiply it by the height of the prism, and we're done. This one, we kind of have to draw it out and think about all of our faces, find the area of each individual face, and then add them together. So triangle, base is 6, height is 4. So 6 times 4 is 24, divided by 2 is 12. So 12 and 12. So we get these 2 numbers. Okay, we know this is 5 times 7. Okay, this one is 5, also times 7. And then this, what would be on the bottom of our prism, is 6 times 7. Okay, so we have a 5 by 7 rectangle. So that's where we get 35. 5 by 7 is 35. And then 6 times 7, which is 42. And we add them all up, and we get 136, in this case, square feet. So it's a 3-dimensional shape, but we're still talking about area, so our units are still squared. Square units, square feet. Lateral surface area would be the same thing. Okay. And lateral surface area, as we're looking at here, if we think of a house and we want to paint it, well, we're not going to paint the roof, the shingles, we're not going to paint the foundation or anything like that. We just need to know the outside walls. So that's what we can think of when we're thinking about lateral surface area. The lateral surface area of a prism is the area of the faces between its bases. So again, lateral surface area, we're not worried about the triangle or the triangle. We would just want to find these three rectangles. That's our lateral surface area. If we're looking at the cylinder, we don't need to know top or bottom. The two circles we don't need to worry about. We just need to know the area of the sides, or in this case would be this rectangle. Okay, so that's lateral surface area. Okay, so Hector wants to paint the exterior walls of a shed. He's probably not going to paint the shingles, probably not going to paint, dig up the ground to paint the floorboards or anything like that. He's probably just going to do the exterior walls, which makes sense. So find the lateral surface area. So we have 10 by 7, okay? 8 times 7, and this side, again, assuming all walls are squares, 8 times 7, and then 10 times 7. Okay? Another thing we can do, so we could look at these as 4 individual rectangles. 10 times 7 is 70. 8 times 7, 56. We can, and then double those, since this wall and this wall that we can't see on the right would be the same. This wall front and the wall in the back would be the same. We could do it that way, nothing wrong with that. Or maybe a quicker, maybe even an easier way to find that is we can, and I think this is how it's referenced on your guys' reference sheet, perimeter of the base times the height. Okay, that will also give us the lateral surface area. Since it's this times the height, this times the height, that times the height, then that times the height, we can just add up those 4 distances and then multiply it by the height. Since, it's going to be 7 feet all the way around. It's not like one wall is a foot higher than the other wall. It's hopefully not. So we add up, find the perimeter of the rectangle. We've done that since 6th grade. So 8 plus 10 plus 8 plus 10. Then we multiply it by the height. We get 36 times 7, 252. And again, it's square feet. So that's another thing we can do for lateral surface area. Again, if you want to add this, we'll go over it a little bit more in class, but if you want to add this to your reference sheet, just so you remember, I believe, I'm actually not sure if it's on there now. So if it's on there, that's fine. If it's not, and you want to put perimeter of the base times the height, okay, that's fine with me, just in case you run into one of these problems and you forget how to do it. And you can always break it apart into a prism, or the prism into a net, and then do whatever sides you're looking for, all sides or all faces of your prism or your 3-dimensional shape, or just the lateral ones that you need to have for your lateral surface area. But if you remember perimeter, that's pretty easy to calculate. Just add up, in this case, the 4 sides, multiply by the height, and we're done. We'll look at those when we return to class, and that is all we have for today. So we'll see you guys soon. Thanks.